Hello and welcome to Subfactors. So today we're gonna take a look at the basic theory of subfactors from the paper, the founding paper of von Jones, Index of Subfactors. So that's a very short paper and extremely well written. So normally it's to be read. I mean, there's no other way of learning these things, and it takes a few days or even maybe a whole week if you want to go through details, but it's really worth it. But now, well, this is the second lecture of our series, and we'll just do it. So I'll try to explain you in 10-15 minutes what all this is about. So let's find this presentation first. Here we are, subfactors and Temperley-Lieb algebras. So there are many things that can be said about subfactors, and I'll try to explain here the main one, the fact that each subfactor produces a representation of Temperley-Lieb. So let's start with some basic stuff. So two factors. These are the von Neumann algebras, which are weakly closed, star algebras of operators, which are infinite dimensional, have trivial center, and most importantly about everything, have a trace. So as basic example, we have the Maria von Neumann hyperfinite factor R. This is obtained as an inductive limit of matrix algebra. So no matter what the matrix algebras are and how you perform the limiting operation, when you weakly closed as to get a von Neumann algebra, you'll get a factor, and that factor is unique. It's always the same thing. It's called R. It's somehow the smallest one. Now that's just one example, but we have also many examples coming from groups. You just take group von Neumann algebras, and in the case where the group has ICC, infinite conjugacy classes, you get one factor. As a common note, these things are related, of course. So when the group is amenable, you get R. In general, it's not known. The classification of von Neumann algebras is of group von Neumann algebras is not known. So it's not known when groups produce the same von Neumann algebra. That's an open problem. People are currently working on, experts in von Neumann algebras. Now, what's the theory of these two factors? There are two things, many things, but two of them, due to Maria von Neumann, are very important. So first of all, the trace is unique. And by trace, always mean faithful positive and neutral trace. So it's an abbreviation, trace. And the second thing is that the traces of the projections can take any values between 0 and 1. So right, the trace is unital. So trace of 1 is 1. So the trace of a projection, you would expect it to be some rational number between 0 and 1, right? It's a rescaled dimension of the range, but actually they can take all values in 0, 1. That's very interesting. It's called the continuous dimension feature of the two factors. Now with this, well, we can talk about the index of subfactors. So a subfactor is just an inclusion of two factors, and the index is this dimension somehow, the big one over the small one. And if you try to define that, you'll get into this Maria von Neumann continuous dimension. So it's between 1 and infinity. It's not an exact number, an integer. Now, what can be said about this in this general setting? Nothing much for the moment. So, however, there is a very interesting result with Wimsner and Boppa. So when the index is an integer, you have a basis, an orthonormal basis with respect to the trace for the subfactors. So that's interesting. Of course, there are some extensions of this to the non-integer index, but you get this basis plus a little bits there that you can complete with. So it's a bit technical, but in the case where the index is the integer, that's it. Now let's take a look at some examples. So once again, it's going to be integer index. Getting out of integer index is really a very tricky business. So at the level of examples and everything, I'll stick to integer index. So first, simple construction, you take a group acting on one factor, you make the cross product. And when the action is minimal, meaning that the commutant of the fixed points is trivial inside the factor, you get indeed a factor, the cross product. The index is n, I mean, very large somehow by n is the order of the group. And it's called cross product subfactor, but actually everyone calls it depth-2 subfactor for some reasons that will become clear later on. So That's an example. Now, another example, we can take once again actions on von Neumann algebras with this minimality assumption. But now I take a compact group, not finite, but a subgroup of finite index. So you see, if I take the fixed point algebras, well, that's going to be a subfactor of index, exactly the index of the subgroup. This is called subgroup subfactor. What else can we do? Yeah, here is a third construction now due to Anthony Wasserman. So if you take, once again, compact group G acting minimally on at one factor P, and this time the extra piece of data is a unitary projective representation. So by this I mean G acts on Mn of C if you want. So you can just tensor P with Mn of C, take fixed points, and you get this inclusion, which is well, the index is now n square. You see, I mean, you have G on top, of course, but here you're large by something having dimension n square, so it's a square of integer, the index, and it's called the Wasserman's factor. And we're not done yet. Here's a fourth construction. Once again, integer index and actually square of integer index. So you see the first ones were constructions, cross products, and subgroup. The index could be any integer. Now, this Wasserman and the subfactors here called diagonal have square integers as indices. So as the idea, we take a discrete group acting on a von Neumann algebra, and the axiom must be altered. That's a bit different. And we take this inclusion, just the NN matrices over the factor, and then the diagonal, but twisted by the generators. Okay. So you certainly get here the fact that it's a factor, it's clear because this is a factor, this is a factor, right? And the inclusion as index n square, because basically you have Q here. That's Q inside the man of Q in a twisted way, but you enlarge by tensoring with the man of C finally. So it's index n square. So what's the conclusion of all this? This is supposed to give you an idea about what a subfactor looks like. So something in relation with groups, but it's not clear. I mean, these constructions go somehow in different senses with cross products, subgroups, fixed points, tensor products, representations, also discrete groups here. So it's, and this is an integer index. So I think the vision somehow is that the subfactors of integer index are somehow a combination of these four examples, somehow unified, and you can throw in quantum groups if you want instead of groups. So it's already very complicated. And in non-integer index, it's a generalization of that. So you see now that's what I was telling you in the beginning of lecture one. I mean, these things are amazingly general. You can see right away here these four basic examples, even if you unify them and you do quantum loops and everything, you will still be far away from what's an arbitrary subfactor. So it's very, very, very general. Okay, very nice. So yeah, modesty in all this. It is very complicated. Now let's see what can be done with the subfactor. So we know that we have this index. Now, von John's discovery, which goes back to the beginning of the 80s and was really amazing, was the following thing, which might look a bit weird, but yeah, that was new. I mean, these subfactors are very old, of course. I mean, people like von Neumann or others knew about them, but they couldn't find anything interesting. So here's the interesting thing. It's called the basic construction. So the idea is that you take A into B, the subfactor, and then you take the projection just from this space B to the space A, everything regarded inside the B of H. So, well, you can extend B then with this projection. Take the algebra generated by B and this projection. So the first result is that this is a factor. So you obtain this new subfactor B into C, and the index is the same. So it's somehow kind of reflection procedure. It's quite subtle. So this is what von Jones calls the basic construction. Okay. Now, if you do this, of course, once, you can do it twice, 3 times, and so on. So you will get a whole tower of factors. Okay, so but let's see some examples first before doing that. So in connection with our 4 examples, if we take a depth to seeing, well, what follows here, the basic construction is a cross product by G hat. When G is abelian, if not, it's G hat, but as a quantum group, so it's very complicated. For a subgroups of factor, it's truly complicated. So in the simplest case, where a subgroup is 1, so the factor is just fixed points, you get this depth to things as a continuation, you see. When you put PGP here, normally, yeah, it can only be the cross product. So this is actually quite complicated, the subgroups of factors. For the Wassermann subfactors, now whose construction looked a bit complicated, this is actually the simplest basic construction. So recall Wassermann subfactors are just obtaining by tensoring with Mn and taking fixed points, G acting on Mn by a projective representation. Well, what follows here is Mn square of P, right? And, this Mn square is just the tensor square of the representation. So this is actually the simplest example. And finally, the diagonal subfactors, so these were somehow Q, but twisted by gamma, side Mn of Q. Here we obtain Mn square of Q, but with the embedding twisted by gamma. So this is a bit like the Wassermann subfactors, but still the Wassermann are the simplest. So see, this, for example, is quite funny. They were complicated in the beginning, but now the Wassermann ones, but actually these are the simplest from this point of view of Jones of basic construction. We'll come back to that later. So anyway, the conclusion of this, you see, in all cases, it's a kind of reflection. Yeah, it's definitely a reflection. So what we had here as evidence for this is that we obtain a factor, so the index is the same. And now I have strong evidence here that it's somehow a reflection of basic construction. So let's see if that is true and if we can exploit that. So first of all, I relabel my subfactor because I have this whole tower that I can construct with it. So I'll denote A0 into A1. I perform the basic construction. So E1 is the first projection from A1 to A0 and enlarge. Then E2, E3, and so on. So that's the Jones tower. And now comes the discovery of Jones. So in this context, E1, E2, E3 generate a copy of Temperley-Lieb algebra. So what do I mean by this? Temperley-Lieb is just take k points here, and strings, joining them, non-crossing strings. Okay, this can be either vertical like this or like this, called horizontal. And, well, this algebra has a very simple basis. That's 2 semicircles and then strings. That's E1. It's called E1. Then string, semicircles, and string. That's E2. String, string, semicircles, and strings, E3, and so on. And the point is that these diagrams here are exactly the Jones projections, meaning that, so first, you want to prove that the Jones projections here in the subfactor context generate the same relations as these diagrams. And that's, well, you see these projections, in the first one is like this and strings, and then you shift. So in the end, the relations in the Temperley-Lieb algebra, you just have to check them in the beginning. It's about the basic construction and maybe the construction performed twice. So you do there some study, projections, everything, a la Murray von Neumann, and you get these relations for Temperley-Lieb in the beginning between E1, E2, and maybe E3. And the rest follows by translation. So you get a representation of TLN. Now, why is this faithful? Well, the thing is that TLN has a trace, a natural trace, which is like this. You take your Temperley-Lieb diagram and you just add things like that. So you get a closing. And the value of that closing is given by the fact that the circle equals n in Temperley-Lieb. So you take n to the loops of that. And well, this is exactly the trace that you obtain in this subfactor representation. So the idea is like this. You have TLN, this subfactor representation, the trace factorizes. But the trace is faithful positive, and that's well known. If something with a faithful trace factorizes, the representation is faithful. That's the idea. Okay, no, this is extremely beautiful. So Temperley-Lieb, I recall you, these are guys from statistical mechanics, so there are a lot of things behind all this. And what should we do first? There are so many things. Well, first thing to do is following Jones. His paper is to prove the index theorem. So when it is less than 4, this representation actually can work out a bit things. It cannot really exist unless n is the square norm of the graph. There's some from Frobenius there, and you get that n must be 4 cos squared pi over n. So there is an index restriction. The index is quantized somehow. So that's an interesting thing. Also, you can go beyond that. I mean, as I told you, the restriction comes from the fact that the index is square norm of the graph, and the graph should be AD, so you can finally classify the subfactors. It's an AD classification. So that's one thing. Now, let me tell you a bit what's going to happen in the next lectures, because this is a bit anecdotal somehow. I mean, what's interesting is to build on this, the fact that you have Temperley-Lieb. So here comes the second main result, which was discovered later by Jones, is that the planar algebra structure of TLN, I mean, just Greek diagrams, possible senses, extends to this to a planar algebra structure of these cometants, meaning that the elements of the cometants are not exactly diagrams, but they behave like diagrams. We can play with them in all possible senses, and that's somehow the idea. Well, maybe an example instead of the definition, an example for those of you doing maybe quantum groups or something like that, that's going to tell you what a planar algebra is. So let's take a Wassermann subfactor, okay? So something like this coming from a projective unitary representation. The Jones tower, as I told you, is going to be something like this. It comes from the tensor powers of pi. Now, if you compute the cometant, so the cometant of this is inside of all these guys, it will just disappear. So finally get the fixed points under G of mn square, mn3, so it's exactly the same spaces. So that's the planar algebra. I mean, for those who know of it, like quantum group Hopf algebras, whatever, a bit of quantum algebra, you probably know that these things you can play. And the elements there behave like diagrams. It's a planar algebra, so that's somehow the idea. And what's the point now of this planar algebra? So getting back to subfactors, they can classify the subfactors. So those having finite depths, meaning somehow that the quantum group is finite, which is there, are classified by the planar algebras. And more generally, the amenable one, subfactors are classified by the planar algebras. Amenable meaning, once again, it's about the quantum group somehow, which is there. And finally, a third thing, once again, due to Popa, so 1 and 2 are due to Popa, 3 also to Popa, is that any planar algebra actually produces a subfactor, and vice versa. Well, the correspondence is not exactly bijective, but these are the results. So that will be the idea somehow for the next lectures to understand a bit all these planar algebras, correspondence between planar algebras and subfactors. Okay, so see you soon.